So what I'd like to do is take you through a couple of stoichiometry problems that use Avogadro's number in them. This isn't terribly common in chemistry because it turns out that in lab it's not very convenient to measure atoms or molecules or formula units either before or after an experiment. And so as much as it's part of stoichiometry, it's not real convenient in everyday stoichiometry in the lab to actually use atoms and molecules in the process like you've seen in lab so far. However, they are important to keep that idea of Avogadro's number in place and as part of what we're studying with stoichiometry and relate it back to the mole. So we're going to do a couple of problems that I'll have you practice in class, including the two that I'll give you examples for in this video and the next one. This is problem number 1 on the page that I gave you in class. And again, if you're not in my class and you want to do this problem along with us, you can just copy it down somewhere. The question asks how many formula units of sodium oxide are produced by the reaction of 1.44 grams of sodium with excess oxygen. Well, one thing you'll notice different about this compared to some stoichiometry problems is that there's no equation. So we need to figure out the equation first. If we take sodium and react it with excess oxygen to make sodium oxide, hopefully as we hear that, it starts to sound like a synthesis reaction. We're putting sodium with oxygen to make sodium oxide, to produce sodium oxide, or make it as a product. And so the reaction equation is quite simple. It's sodium plus oxygen gives us sodium oxide. So the equation would look something like this, right? Sodium plus diatomic oxygen gives us the sodium oxide as Na2O. Be really careful with those formulas again, as always, to make sure you've used oxidation numbers and crisscross them down or otherwise come up with this formula for Na2O. Now, we need to balance the equation in stoichiometry, of course, and this isn't a hard one to balance, so I'm just going to throw the coefficients on there for you. The colors are there just to help us kind of make this pop out later in the problem, so don't worry about the colors right now, but 4, 1, and 2 are the correct coefficients for this particular reaction equation. So, as we go on, like with any stoichiometry problem, you'll start with the one value that you're given, 1.44 grams of sodium, and that'll go in the first box. Now I apologize that I don't have my writing tablet along with me today, or I would write these out by hand, which I think most students prefer, but as it is I don't have that along, and I need to get you a video or two for practice and for examples, so I'm going to just put these up as animations instead this time, so forgive me for that. But we're going to start with 1.44 grams of sodium in the first box, and as in all stoichiometry, if you're not in moles at the beginning, you need to convert to get there. Well, we're not in moles, we're in grams right now. So to convert grams to moles, as always, we put 1 mole on the top. In this case, it's 1 mole of sodium. Whatever unit you're trying to convert to should go in that top position. And underneath, something that makes it a true statement. 1 mole is equal to, or 1 mole for every what? Well, in this case, we stick with the idea that whatever units you have on the top left corner, in this example, sodium oxide here, whatever units you have there, grams of sodium, those need to come down. And so grams of sodium will come down, and from our periodic table we can get 23 grams for 1 mole. That atomic mass that we're used to for sodium, you don't even have to add anything up because it's just plain old sodium. So for every 1 mole of sodium there are 23 grams of sodium. I'm not going to cancel the units out on the screen here because it makes it harder and harder to read for you, but the grams would cancel out now and we'd be left with moles. The next step in stoichiometry, as we've done before again, is to set up a mole ratio. Keeping in mind that whatever units we have on the top in the last position here should come down and to the right, we're going to bring moles of sodium down and to the right, and that'll fill in the bottom, and we're going to put a 4 in front of it because in the balanced equation it says there are 4 moles of sodium used for every 1 mole of oxygen to make 2 moles of sodium oxide. So that 4 coefficient comes down and shows up here again. Both 4s in red, just to kind of remind you where that came from. And in this question, you're being asked how much or how many formula units of sodium oxide. So we want to use Na2O on the top of this ratio, in the mole ratio, because that's what we're trying to convert to. And so in this particular equation, for 4 moles of sodium that you put in, you'll get 2 moles of sodium oxide back out. So this is a 2-to-4 ratio. And as always, that would be true upside down too, but then the moles of sodium wouldn't cancel out. So we've got moles of sodium on the top, and then now on the bottom, moles of sodium again. Those would cancel out, and you'd be left with moles of sodium oxide, which is just about where we want to be at the end of this problem. The last step of stoichiometry, if moles isn't what you're looking for, to convert those moles into what you are looking for, and in this case, that's formula units of sodium oxide. Remember, formula units fall under the category of particles, and so we use Avogadro's number here. For every 1 mole of sodium oxide, there are 6.02 times 10 to the 23rd formula units of sodium oxide. And as usual, we try to keep those units diagonal, so moles of sodium oxide is on the bottom, in this case 1 mole, and on the top 6.02 times 10 to the 23rd, 4 units per mole. Don't forget, folks, every time you're doing one of these, when you're making a simple mole conversion, as we are at the beginning, we use 1 mole, and as we are at the end, we use 1 mole, because then the 23 grams is correct, and the 6.02 times 10 to the 23rd 4 units is correct. In the middle, those coefficients from the equation mean that the numbers in that middle mole ratio can be anything. All right. So as this is set up, everything would cancel out: grams, moles of sodium oxide, and we'd be left with 4 units of sodium oxide. You want to punch that into your calculator, and if you're careful with it and use parentheses on the numerator and the denominator to do your division, you should end up with 1.88 times 10 to the 22, or 10 to the 22nd, 4 units of sodium oxide. That's got 3 significant figures, just like my original number did, and it turns out everything else along the way in this problem had 3 significant figures as well. So 1.88 times 10 to the 22nd, 4 units of sodium oxide would be correct. So that's a stoichiometry problem using Avogadro's number. I'll go through problem number 5 on this same page for you and record a video that you can watch as well if you'd like. That one also will tie in volume and liters so that you can see a little more variety with that too. So hopefully that helps, and good luck with the rest of the problems. If you're watching the other video, I'll see you there.